Okay, hello again, everyone. I just finally got my whiteboard up on the computer. Somehow it's very picky. I hope you can hear me well. Please type something into the chat so I know that you can hear me. Well, good. Cool. Thanks. So let's get to the business right away. We have to continue talking about the neural nets today. And I will be sharing you the slide which we started, actually the board which I've started working on last week. Okay, good. I hope you can see it. So basically, we talked about the toy neural net. This is it, and the toy neural net basically has a couple of layers. So two layers have associated weight matrices. So we have activation number 0, which is equal to input vector. We have activation 1, which is composed of the multiplication of a previous layer with weights, summation in the neurons, in the corresponding neurons, and then the activation output. Basically, this is activation number 1. Then we have the output layer. So this is basically activation number 2, which is sequentially being calculated like the previous one, and basically it outputs whatever it receives. Right, okay, so we looked into these things. So basically we have a couple of matrices of weights which we need to estimate throughout the training process on the network. And this is called two-layer network because the first one is just a 0, it doesn't count. Okay, so basically for the training steps, we looked into the 3-step propagation. So the first step is basically forward propagation, where we move values forward through the network. So basically calculate from the input vector the output vector. Currently in our toy network, we have an output vector composed of a couple of elements. So basically y1 and y2. And this can be as an example, the coordinates of something in somewhere, right? So navigating robot indoors, right? So basically navigating over the radio frequency signals, for instance, and the network need to input various sensor information and output the coordinates, so robot will know where it is. Okay, so basically we have a forward propagation, which is equal to the prediction, when we have a total error calculation, which is basically a summation of the local errors, and the back propagation, which is basically a learning process. So we will be looking into these. So each neuron is composed of the activations that go in. So we have a net input, which is a ZEF value. And we basically apply an activation function, which is an application of the nonlinearity into the network. So basically, this is an output, right? Rather simple. Net input calculation is basically a multiplication of a couple of matrices, matrix and vector. And basically, then we have a activation calculation, but just by applying an activation function on the result. So basically, this was the few steps of the forward propagation. We had in A0, Z1, A1, Z2, A2, and the final A2 is equal to the output vector. Okay, these were various dimensions, matrices. Oops, I need to undo somehow. Okay, maybe it's more or less in place. Okay, then we have looked into some error calculation. This is a simple approach that we are looking for the calculation of the regression. So basically, this is sum of squares. So this is our error, and the total error is basically calculation of these the sum. Okay, so this is where we are. We have to look into the backpropagation. So let's go into that. So for the backpropagation, let me see if I have it correctly defined. No, it's not correctly defined. So I need to disconnect my whiteboard and connect it back again, because sometimes it gets just offset and I can't draw it. Usually physical reconnection helps. Let me try right now. Okay, so basically sharing again. Sharing again. Okay, let's see if I can draw now. Yes, I can draw it now. So usually this is my usual routine. I have to reconnect that guide in order for it to work correctly. Otherwise, it just gets a huge offset. Okay, so backpropagation. So what we will be looking at, we will look into the generic form and as well into the specifics for our toy network, because the generic form just requires so many indexes. We have a complicated structure right there, right? So many, there's a possibility to have lots of layers, lots of neurons within the layer and so on. So in some cases, I will jump from the generic form into the specific form, because the specific form is so much simpler. Okay, so in the beginning, let's define that capital L is number of layers. Right? So we will have from 0, which is an input layer, right, until 1, this is a normal first layer, and until capital L. Right, so capital L is just basically a number of layers. So for the indexing and basically defining any layer, we will use a lower L. So this is basically some layer. Right, so lower L is just some layer. Okay, so what we will be using quite a bit, this is on a side, I need to write it down, that we will be using the so-called chain rule in order to calculate the derivative of compositions, of function compositions. So basically, if we have a situation that z equal to function, right, which takes an input output of the other function, right? So something like this. This is a so-called composition. Remember when I just was telling you about the deep learning. So deep learning is basically embedding functions in a manner of like this, right? So basically the derivative, partial derivative of x on this function, right? So how much change in x actually changes z, right? The final result is calculated so that we have a derivative of y in z multiplied by the derivative of y with respect to x. So this is so-called the chain rule. So this is how we can basically decompose a complex function in a manner that we have a product of derivatives. So basically product of derivatives then represents the final derivative, and we can basically find the derivative within the chain of various functions. So what we will be doing, we will be using that quite a bit. Okay, so basically, and again, another thing, I just for the notation, so we have error, right? We have an error, and we will have an I, right? So I is the observation index, right? Like xi, yi. So we have an observation index, right? And then we have an f, let's say. So this is the local error, right? So this is a local error, or the output neuron number, right? Number. If we have in our toy network, we have 2 output neurons, so basically it will be 1 and 2. Okay, and when we have a derivative with respect to some weight, right? Some weight. So this weight is coming from the layer. This is a layer number, just like we defined right there up top, right? And this is an E and I need the letter E and J, let's call, okay? So E is the number of node in L minus 1, right? In layer minus 1, in layer just before this weight. And J is basically number of node in L. Right? So basically, connection between 2 neurons on the adjacent layers is connected via some weight. So that's why we need to look into these things. Okay, sometimes we will be looking into the local errors. Sometimes we will be looking into the global errors as well. Okay, so this is more or less the notation. We will go through these notations quite a bit, so keep tuned. Okay, so basically, backpropagation is step number 3, so we will be dividing it into these substeps. So the first substep is 3.1, right? We will look into the case, then L layer is actually the final layer, right? The output layer. So these are the weights, what we will be looking at, the weights that are immediately on the output layer, right? Okay, oh, that's so far away, the network. Okay, so basically, this is the error we have calculated, right? We have summed up. And basically, we have weights immediately for the output layer. So this is one case. This is a simpler case when we need to backpropagate weights. So basically, we want to update the gradients by gradients with weights, right? So we update them. And later on, the second case we look at are the further weights deeper into the network. So it will be a little bit more complicated, but basically just the same thing, right? So that's far away. Okay. Okay, so let's take a look. So how do we calculate the local error, right? The local error is calculated by 1/2, right? So we basically have defined for ourselves the error function, right? This is half and the difference squared, right? Half of the difference squared. So here we have yi. This is the true value that we're looking for, right? This is the trainer. Then we have the activation function on the final layer, right? So final layer activation function, we can put something like that. But this is the activation function, right? Then we have the W of L, right? The final guys, right here. Okay, and just basically I have not used the transpose before, so I will not use it here, but usually it might be required. It's actually up to the actual configuration, right? So I will not be using it here, so to not confuse you anymore. Okay, and this is multiplied by the activations coming from the layer before that, right? So okay, so this is what we have. So what actually we have here is that we have the ZEF calculation, right? So this is the ZEF calculation. This is the activation calculation, right? And this is the calculation of the error. So as you can see, this is a composition of functions, just like we saw here, right? So what we can do, we can just try to start decomposing this, and finding out the derivative of the specific weight, right? So our derivative, I think we can do this right away. Okay, let's derive, for instance, E1, right? So this is the first I1, right? So for the first output neuron, right? For the first output neuron, we will be using the our toy network right now for the simplification, right? And W on weight on the second layer, right? This is output layer because capital L equals 2 in our toy network, right? And let's take the 0 to 1, right? So we basically will try to back propagate. Oh man, it's so far away. I need to copy it over. We will be back propagating, right? So from this local error, this weight, right? Because this is a weight, which is on the second layer, 0, right? 0 coming from here, and 1, right? So this is this relationship, this connection between the two neurons is actually corresponding to this weight. So we will be looking how to backpropagate gradient for this specific weight as an example, right? Okay. All right, so let's do it. Let's do it. So by using the chain rule, we basically have the derivative of I1, right? So this is the error function, right? And with respect to A, 2, and 1, right? So this is this guy, right? So this guy is an argument into the error. So that's why we're deriving error with respect to this argument, right? Now we just multiply, this is by the chain rule, by this 2, right? So this is that part, the activation function, right? The activation function part. And now we have a net input into this activation function. So this is the net input, the ZEF part, right? So we multiply by the ZEF part. And now we just take the ZEF part, 2, right? Net input, and with respect to, we calculate the derivative with respect to 0 and 1. This is exactly the same weight we're looking for, right? We just got to the weight that is of our specific interest right here. Okay, so now we can look into each part separately, and then we just put them all together. Right, so basically the first part is just a derivative of this guy. Right, so let's take it, copy. I have the technology on my hands. I can't paste it like that, or can I? No. Okay. Paste. All right, so I think I would rather just basically write it again. It should have been much faster. Okay, so this is the derivative of 1 second yi 1 minus a1, and this is all on the second, and these two guys are squared, and this is the derivative of this term, right? So by taking the derivative, we basically 2 goes here in front, so it becomes 2 and 2. These two guys go away, right? The inner, everything here, it need to be repeated. I1 minus A1 on the second layer. And since we are deriving, this is our variable, right? So this is the variable, it becomes minus 1 times minus 1. Okay, so times minus 1. So basically this becomes, we can change these guys places. So A1 2 minus yi1. Right? So this is the derivative for the first part, right? We just found it. The difference between the output from a neuron and the actual value from the data set. All right. So now the other part, the second term, right? So this was the first one. Now we will be looking at the second one. So this was the first one. Now looking at the second one. So this is derivative of activation on activation with respect to the net input, right? So this is something like this. So this is basically the gradient, right? So we have not gradient but activation function, right? So this is activation function. So we just do not define right now which kind of the activation function it is. We will be talking about this later on. I will tell you about various aspects of using. So we can mark it as the derivative of activation function, right? So let's put it like this, Z1, 2, right? So we can leave it like that for now. Later on, we will look into various activation functions and their derivatives. Okay, and number 3, this is number 3, this is this part, right? This is number 3. So number 3 is basically we need to take from the net input, right? Net input, we take the weight, which was, in our case, it was 0 and 1. 0 and 1 on the second layer. So basically, this is a derivative of sum j equals 1. So we basically loop over all the activations from the previous layer, right? So this is index of them, and this is basically JFs, right? So something like that. Not Fs. This is 1. This is J. This is where it's coming from, which neuron is coming from, and it's coming to 1, right? This is coming to 1. I started writing to generic form, right? This is the layer. This is the layer, and it's multiplied by the activation of JFs, right? Activation coming from JFs and from layer L minus 1, previous layer. So this is the actual formula, right? The formula, not in the matrix notation anymore, but we have seen these formulas quite a bit because this is just a vector multiplication. So what we can say is that all the A's and W's are being the constants, so everything just basically go away, right? Apart from the W0 and 1, right? W0 and 1. So what we have here is that we have A0, right? A0, so 0 and 1. So this is the only one which is important, and it's multiplied by 1, right? So L minus 1. So basically, the derivative of this guy, of this multiplication, is just an output of the activation, right? So since our A0 is biased, so it's obviously 1, right? Just the value of 1. But for now, this might be the generic form. Okay, so all these guys can come together right now, right? So writing it back into the generic form, so what we can say that the derivative of Zef, oh, sorry, not Zef, I'm writing the wrong thing. Okay, I need to write the final form, right? So the derivative of error with respect to some weight, which we will define E and F, right? Because it's an F's neuron, right? It's an F's neuron connected, is equal to AFs, right, on the final layer, minus YIFs, right? So this is the first part. This is the first part, which is what we calculated, right? So it's the first guy. Okay, so this is the first guy. Again, I'm just writing for you. This is the first guy times the derivative of the activation function, right? So this is on the ELF layer. This is the second guy, the second part. This is the second part, right there. Okay, and times the activation, which is connected via this weight, L minus 1, right? And this is the third part. Okay, so basically this is the gradient. This is the gradient that we have for a specific weight on the output layer. If we would look at right there, you can see immediately that for the specific output neuron, right, for the specific output neuron, we have used the local error. This is the one thing, right, which you need to know. Only local error is important for the output neuron if you calculate the immediate weight, right, because it does not depend on this error anyhow, right? It depends only on this error. So we need to backpropagate only this error. Okay, this is one thing to take away. The other thing to take away, that the difference, net input, right? Net input is the only difference. The first and the second part of the derivative, right, in the chain rule is actually just the same for all these weights that connect to the neuron, right? So basically we have 3 connections to the output neuron, 1, 2, 3. And all the weights share this one similarity, right? So this is one similarity that is shared between these gradients. So this similarity, the same thing, is just this part. The first and second, it is always the same. So we need just to multiply this exactly the same thing with the activation values, and we will get gradients for all the weights that connect immediately to this output neuron. So this part is called delta. And this is a delta of the F's neuron on the ELF layer, right? So this we will call a delta, and this is usually called a delta rule. Right. So this basically backpropagates the difference which was accumulated by all the inputs on the specific neuron on the specific layer. Right. Okay. So basically our gradient then on the final layer becomes W, E, and F. Right. So E and F on the final layer becomes equal to epsilon. This is the learning rate. Remember, this is the hyperparameter multiplied by the delta of the F's, which is connected to the F of the F's neuron, right, on the L layer, right, on the final layer, times A activation, which is coming from the EVES, right? EVES neuron on the layer before the final one. So this is basically the gradient, quite simple. This is the gradient. So what you do, you just basically add it up to the weight that you had before, and you have the difference. So basically this is how neural network can learn. Okay, so this was an immediate guy, right? Let's now take a look into the guy before that. So we want to backpropagate all the differences, right? So to backpropagate all the differences, we will have 3 times 0.2 step. This is when L does not equal L. So this is a hidden layer. So we will backpropagate gradient, backpropagate change to the hidden layer, right? To the neuron which is covered by some other neurons, by some other layers. So it's not it's not important which layer it is. We will see that the formula is just the same. It's universal formula. But for now, let's write down it as our toy network example. So okay, now we have a total error. So in order to calculate to backpropagate error, now we need to accumulate all the local errors into one, because this is important because it's all interdependent. So we have a total error. Now the derivative with respect to the weight, for instance, 0 and 1, right, on the first layer. So what we do now, we will look on the weight which is connected from the input layer to the hidden layer in our toy network, right? So we will be looking into this guy. I think what I will do, I will actually copy it over and take it lower, because it's just so tedious to go forth and backwards. Okay, let me try doing this. Okay. Okay. Now copy. Okay, I hope I copied it. All right, so now let's go back. Let's go back and let's put it somewhere right there. Okay. Yep. Just landed up somehow a little bit on the side. Let's try to arrange it a little bit better. Okay. You just go over right there. Okay. Okay. Okay, so in our first case, what we looked at was the weight of this connection, right? Now we will look into the weight of this connection. So as you can see, this connection is actually dependent on these guys, right? This guy and this guy. Right, so this connection is required that everything accumulated. So basically, it is dependent on these two, right? Beforehand, it was dependent only on this guy, right? Okay. So let's now try to write down how it looks. So basically, this error is just the derivative of on error, right, on total error, and we will put the net inputs on the second layer. Let's make it a star, right? Let's make it a star, because we want to calculate the influence of the all the net inputs of this error, right? When error is being populated on all the net inputs on this guy and this guy. And actually, as you will see, and we've been doing that so far, right, that this is equal to the delta of all the output neurons, right? All the output neurons delta. So this is actually equal just the same term as we had over here, right? It was composed of 3 parts, right? 3 parts. So by decomposition, we have error and net input, right? So 1 and 2, error and net input derivatives, right? So error and net input. So we have delta rules here. right? So by delta rules, we already halfway through the output layer, right? Halfway through output layer. Okay. So now we have the derivative of the input, net input, star, right? Again, all the net inputs on the second layer, And here we have an activation on the first layer, right? And 1. Activations on the first layer, right? So we need activations on the first layer to be backpropagated, right? So this is equal to W1, which is connects to the second layer, on the second layer, right? And now we need to take this activation, which is coming out of the first layer, activation which is coming out of the first layer, activation on the first layer, and we want to reach this weight, right? Since we want to reach this weight specifically, so we are interested only in this neuron right now, right? We can leave this guy behind. We just want this guy now, right? So basically for this guy, we have, and again, the activation of this, right? Activation, and now we just reaching out the weight. Sorry, not like that, the weight itself. Z1 and 1, and this is our weight of 0 and 1 on 1. Okay, so net input. So what we wanted to have, the net input on both these two guys, on both output neurons, coming from this activation, right? So this specific activation. So this is what we looked at, right? And then we looked into these and these. Okay. So basically, this is the chain rule which we constructed from the error through the delta rule on the output neurons and gone through to the actual weight now. Okay, so these two things are familiar. This is the one which we need to accumulate. As you can see, we have a star here and the star here until we reach the activation on the first layer. So basically, we can rewrite it in the form now, because we already have everything we require. W0, 1, and 1, this is the same guy, right? So what we need to do, since this is a star, so we need to sum up all the deltas. Now, J equals 1, and this is the length of the final activation. So this is basically number of neurons on the output layer, right? We are going on number of neurons on the output layer. So what we do, we just take delta of this, right? We just take delta of this. This is the first part, right? We just take delta of this, and we multiply by this guy, which is the weight, only the weight. Because the derivative of the net input with respect to the activation is the weight, right? So this is basically derivative of the ZEF, let's say on the second, right? First, with respect to the A first one is basically W on the second, right? Times activation on the L minus 1, right? So basically this is a multiplication again, but since now all the weights are constant, so basically these guys go away because we're summing it up, and only the weight, the one of the weights which is connected directly to the activation remains. So this is the result, right? So what we do, we basically do this right there. We just multiply all the deltas from the output layer with the corresponding weights. So since we're going to this weight, we take deltas, multiply by this weight and this weight, right? And sum it up. Okay, so we basically have calculated everything. So now what we have here, this part, this is the with respect to the activation, just like we had before. This is the activation on the first layer derivative with respect to the ZF11, right? So we basically multiply by the derivative of the activation, 1, and then we have the same guy, right? So this is again, this is the same multiplication of couple of vectors. So what we have here, we just have a 0 and on the 0, right? This is a0 and 0. In our case, this is a bias. This is just 1, right? In our case, this is just 1. Otherwise, this would be the element from the input vector. Okay, so this is basically the calculation of the propagation of gradient through one and through the couple of layers, right? Through the couple of layers we just gone through and reached the required weight, and we have the gradient of it. So basically, if we look into more precise way, we see that this part is again the delta rule, right? The delta rule on the L flare, and this is not the L flare. This will be the delta rule on the specifically first layer and the first neuron. Delta rule of first layer and first neuron. So basically, this is again the error, part of the error which got propagated through this specific neuron, right? And when you want to reach these, you basically recursively calculate these deltas throughout the network. So the generic form of this would be, let's write it down, WEF L, right, would be equal, this is the weight that connects E and F, right? E and F would be the sum of all the J equals 1, and this is A L plus 1, the next higher up in the stream layer neurons, right? And what you do, you basically multiply the neurons up there, right, with deltas and WFJ L plus 1, right, all the weights. So these are multiplication of the previously calculated changes, right, on the previous neurons. And now you have it all calculated. Now you basically have the derivative of the on the activation times the activation on the previous layer, right, L minus 1. And this can be rewritten in the more concise way. This is delta on the L layer, on the current layer. So we basically reach the immediate neuron, right? Immediate neuron, and we just basically multiply by EL minus 1. Okay, so basically by calculating these delta values, we can reach any neuron, any weight in the network and do the update. So this is a recursive operation. Recursive, basically multiplication, summation, etc., and it reaches all the weights in the network. Okay, so now the gradient itself, right, of the E's and F's on the L flare is equal, again, epsilon. This is the learning rate, hyperparameter. This is just again, and the delta L F's, right, the delta then multiplied by the activation, which goes in, right, into this weight. And basically, as you can see, this gradient is just exactly the same that we had over here, right? It's just exactly the same. And this is just an illustration that by calculating a simple delta rule, delta value for each of the neurons, you can basically back propagate this error, error on the gradients, on the weights, and do the updates, right? At first you forward propagate, then you just basically back propagate everything. Okay, I hope you have understood the mechanics of it. More or less, and this is for the simple network. Now, what we basically miss in our calculations. So basically, we have these activation functions, and the derivatives of them. We just assume that we just take from somewhere. So now let's go and create a new whiteboard and start looking into specifically the activation functions. Okay, so I will give you a list of various activation functions and we'll give you some recommendations. So activation functions, right? So activation functions, basically historically, as I have already told, we used it at first. It was quite simple activation functions and then became it more and more complicated. So let's go from the simple ones a little bit in a historical way, and let's look into these functions, right? So the first one is the binary step function. Binary step function was a function used in the perceptron. So basically, this function, which is jzef, zef equals to 0 if x is less than 0, or 1 if x more or equal to 0, right? This is the classical way. Of course, you've seen the function of in the classical way. This should be -1 and 1, but there are various options of it. So the derivative of this function is actually 0 if x not equal to 0, right? Or if x, I have written x, okay, this need to be zef. This need to be zef as well. If zef not equal to 0, and undefined if zef equal to 0, right? And undefined. So basically, this is something that can be drawn like this. We have zef net input, and this is output activation for the neural net. You can imagine, so it would be all zeros, then a jump, and then basically goes like this, right? So the derivative would be always 0, right? So this is j and this is j. Okay, so this one is not used in modern networks, right? But worth mentioning. Okay, so number 2 is the linear neuron, linear activation function, and so linear neuron can be called like so jzef equals to zef. So what receive is what's being passed, and the derivative of this zef is obviously equal to 1, right? So basically, then the graph of this would be we have any value on zef is equal to any value on the output as well, right? So like this is an activation, and this is a j, and the derivative is basically equal to 1, right? So this is j like this. All right, so this has some features. This is a fast neuron, right? Because nothing has to calculate at all. It's used on the linear regression, right? So the features is fast because no calculations. It's used for the linear regression, right? And basically the usage on output layer in regression task. If you are doing regression with a neural net, so basically put the linear neuron on the output layer. So whatever is being calculating by the previous output and all the weights is being passed through the neuron. And you can expect values changing from -infinity to +infinity. This is exactly what you would expect in the regression. All right, so this basically, if you would use these on all the neurons in the network, so basically what you get is you get the linear regression. So basically it would be a complicated machine for the linear regression because all the networks you just basically can collapse into a single layer, right? Okay, so this is only on output, not in hidden layer usually is used, right? So basically if you're doing a regression again, use that for the output layer. Okay, so this is just basically implementation of the linear regression, and if your data would be linear separable, then you can construct the neural net completely off the this kind of activation functions. Okay, if your data is a little bit more complicated, so you basically can use the sigmoid obviously, right? And the sigmoid, as you've seen already, we looked on various occasions in the logistic regression specifically, is 1 plus e minus f, right? So this is a function, and the derivative is basically equal to jz, right? The sigmoid, and 1 minus the sigmoid, right? And 1 minus the sigmoid. And the graph is just basically your neuron would act as the classifier. This is an A. It would basically start on the output. It would start normalizing whatever it receives into the 0 to 1 space, right? Just like a normal logistic thing would do, right? So this is a 1, this is 0, right? So all the output you would be putting into the neuron from -infinity to +infinity, whatever value, output would be squeezed into the 0 to 1, right? Space. Okay, so basically the derivative is just like this. So it starts going up and then start going down and then goes to 0. And so this is the function, this is the derivative. Okay, so historically, as I told you in the history, it was used for overall everywhere in the neural net. So now it has been proved that it has problems because gradients get saturated on the high end and on the low end. So basically, then you have a situation when lots of values are going to the negative space. Your neuron will always be outputting 0. And these neurons tend to mask the gradient. So basically, when you have a backpropagation, you can see that you are basically, what you do, you just basically multiply the gradient in the delta rule, right? In the delta value multiplied by the derivative of the activation function. So if you basically would be multiplying by 0 or very, very small value, you would be backpropagating something which is very, very small or just 0. So if you would be starting using sigmoids on the hidden layers, so what most probably you will be getting into is the vanishing gradients. So gradients would be just going away, and you would be training mostly the upper layers, right? The output layer, the one before it, but the gradients on the first layers will not get any updates at all, this might be the case if you would start using the sigmoids on the hidden layers. So basically, features, this is slow, but it's smooth, it has gradients all everywhere, right? They might be small ones, collapse. The other problem is that the center is 0.5. Center is 0.5 when initializing values in that are centered towards 0. You get lots of values basically squeezed away, gone away. Usually in the neural nets, activation functions that have mean output on the on 0 act much better, right? They do not have this tendency to basically wipe away everything which is going below. Okay, so basically this has problems. This has problem. Everything on output is on the plus side, and saturation of gradients on both ends, basically. Yeah, vanishing gradients, exploding gradients, these are the problems with this guy. So usage is mainly on output layer. Output layer and for classification. You have a network, and throughout this network you pass values, and at the end you basically pass through the sigmoid, and then you get the prediction, right? You get the probability from 0 to 1. So you want whatever values you get from the network, you want to squeeze into the range of 0 to 1. So this is totally being used on the output. Then you have a classification task. All right, so this is a sigmoid, usually not to be used on in the hidden layers. Okay, so four. In order to avoid these problems with the saturating vanishing gradients, it was invented with tan H, or the hyperbolic tangent. Okay, function, which is basically have corrected some of the problems that came with this sigmoid. So this is a little bit more complicated. Zef minus E minus Zef divided by E Zef plus E minus Zef. And the derivative of this activation function is 1 minus G Zef squared. Okay, so basically now what you can see that this hyperbolic tangent is actually you have net input, you have the output activation, and here we have going like this, passing 0, and then going like this again. So it's shaped just exactly like sigmoid, but the difference is that it goes from -1 until 1, and it's zero-centered. It's zero-centered. So this is one good thing, that it's zero-centered. When you initialize weights, when you pass values through, they are usually zero-centered, right? The mean is on 0. So basically it has all the capability of passing gradients and calculating values on both ends. So this is good. It is symmetric on 0. The other thing which is good, that it has more power, right? The power is basically coming from the -1 to 1, right? It has the larger range on the output, as well as gradient is higher up, obviously, right? Because it's going from -1 to 1. It's higher up, right? The gradient. So this is J and this is J, huh? Okay, so this again slow, because it requires some not simple calculations. All the good things, more power, zero-centered, it does not saturate that fast, right? So you can expect that gradients are being passed to the upper layers. So everything seems to be fine. And usage of this is basically in hidden layer, in hidden layers. In hidden layers, it was told. I remember when were defenses on master physicists. It was always telling students were always telling that tan H is a default on the hidden layers, but this is not actually true. Recently, it was before, but not now. It's not true. On the hidden layers, we have a different guise. So this is quite rare to use tan H on the hidden layers from the recent literature. Obviously, you can put this guy into the output layer as well if you need output from -1 to 1. I haven't seen that, but this is obviously a possibility if you expect output from -1 to 1. Okay, so after this tan H was invented, the new invention was actually to use something simpler, but not less powerful. This is basically a rectified linear unit. ReLU, or rectified, or corrected linear unit. And this is a rather simple function. JZEF equal to maximum from 0 or ZEF, right? So it basically takes a 0 on negative sides, it returns 0 on negative sides, or either on positive side, it returns ZEFs. So basically the derivative of this guy is equal to 0 if Z less than 0, right, on negative sides, and 1 if ZEF more or equals to 0. And now we can basically take a look into the function itself, how it behaves. So this is ZEF and activation output. Okay, so it goes like this. It just returns 0 on all the negative values. And now it starts to return itself, right? Okay, so this is the J, and the derivative would be basically going 0, and here we just start outputting 1, right? 1 multiplied by 1 multiplied by 0. You can imagine the gradient, right? If the gradient goes back, right? Okay, so this is 1. Okay, so this is the guy. Okay, so this one does not saturate, right? It does not saturate. It is fast, right? If you need a fast convergence, if you need a fast network, if you want to calculate something which is fast, this is the choice number 1. Basically, if you want a fast calculation, this is what you choose to try it out. Then what it does basically, as you can see, it goes 0, right? So basically your neuron can start outputting 0, right? If the negative input is put into the neuron, right? So you can imagine that in some cases, neuron just stops outputting. It is just outputting 0, right? So you can imagine that your network becomes like a set of gates. And when you do a classification, for instance, and you have an input of some vector, so on a certain conditions, neurons start to be switched off and others are switched on. For the other class, other neurons start to be switching on and switching off. So basically, the network becomes like a network of gates. On and off, on and off, on and off. And this appears to be working very good. So basically, then you just have on-off network, and it gives to the network so-called sparsity, that neurons get switched and get switched on and off on a certain conditions based on the input. It is very convenient. But what this guy has one problem, that if some neurons just die, right? Some neurons just die and do not recover. You can imagine that when you are training neural net at a certain conditions, right? So your all the inputs into into the neuron becomes just negatives, right? Negatives. So basically, when you backpropagate everything, you can basically get blanked, right? You just don't update weights anymore, and you don't get anything. So parts of the network, neurons or just parts of the network, can just basically die out. So this is the problem, that dying, it's called dying ReLU. That basically it switches off neurons, and these neurons do not recover, right? So it's good, like it acts as a gate, but at a certain conditions. If weights become just overly large, right, due to some condition or negatives, right, they just basically negative, become very low, actually low on the negative side. So basically they just switch off neurons, and these neurons never come back to life. Okay, so dying ReLU problem. Okay, so the usage, hidden layer. Okay, so basically to solve this dying ReLU problem, dying neurons problem, researchers have discovered that there could be a solution for that, and the solution is so-called leaky ReLU. Leaky ReLU problem, rectifier linear unit, that basically leaves the possibility to leak a little bit the neuron, right? Some small value to leak out, so that it could recover after a while. So basically this becomes a function like this. So again, we have, like in the simple ReLU, classical ReLU, we have a maximum between alpha times z and zef. And this alpha is the hyperparameter you have to choose. So the gradient basically becomes alpha if zef is less than 0, or 1 if zef more or equal to 0. Okay, so basically now for this activation, we have a situation like this, that basically we have just the same situation, the linear output. Whatever is being accumulated, whatever is being summed up, if it is on the positive side, basically it's returned as is, right? So this acts as a, for instance, as a linear regression, something like that, right, on the positive side. And on the negative side, right, it just returns some small value, right? So this small value, returning the small value, as you can see, gradient is alpha, right? Gradient is not 0. This means that once the gradient back populates through this neuron, it leaks. It leaks a little bit. It leaks like alpha. As you have seen, there is delta multiplied by the derivative of the activation function and then multiplied by something else. So this alpha allows some value, some small value, to leak through this neuron on the backpropagation task. All right, so basically this allows for the neural net, a single neuron or the part of a neural net actually to recover, to start outputting something again. All right, so this is a J, and for this guy we have 1, and here we have alpha, right? So this is alpha, and this is 1. Okay, so this is a derivative. So again, leaky ReLU, is the better version of the ReLU. It has a hyperparameter, which is not a good thing. It allows to recover. So basically, again, this is a fast calculation. This is does not die or allowed to recover, right? Allowed to recover. Basically, what to say more? So alpha is, for instance, 0.01 is a small leak. You can go with the default parameter, right? So alpha equals 0.2 is the huge leak. So this is a hyperparameter that you can go with the default, obviously, for your task on a more complicated tasks, which is basically you need to monitor what's actually happening. If you see that you have some neurons not outputting, not actually working, okay, gradients do not propagate to the on a lower end, on the left side neurons, right? So you basically might require to increase a leak a little bit, so the gradient is getting passed. Okay, so this is again the usage on hidden layers. Right? On hidden layers, this is the usual thing which is to be used. Okay, so other things which I can mention, there are something like up to 10 maybe various ReLUs. I just would like to mention a couple of more. So one of them is so-called R leaky ReLU. So basically this is randomized leaky ReLU. So as you can imagine, this is then alpha picked randomly. So basically, the leak on backpropagation is being picked up randomly, right? In a range, in a given range. So you can pick a range, for instance, from 0.01 until 0.2, right? And you would like it to be random. So this gives some non-linearity to the network. And on predictions, it is being average, right? On prediction average. So basically, if you have an interval, it has been selected randomly. On prediction, it is fixed on an average value. So this is, again, some nice thing to have, maybe to try it out. A little bit more complicated in computation, but yeah, you don't need to take the parameter, to select the parameter. So basically leave it to a network. It's more loose, the decision. Okay, so the other one is so-called the parametric leaky ReLU. And then alpha is being learned during training. So as you can see, researchers want to get rid of various hyperparameters. So one of the ways to get rid of the hyperparameter is basically try to learn during the execution of the network. So yeah, this is one of the options. Okay, so alpha might be another weight which is to be learned throughout the network. Okay, so the last one, I think this is the last but not least activation function which I want to mention, and this is actually a recommended one. The previous ones would be used on the hidden layer as well, as you can imagine. The exponential linear unit or HALU. So this is the I would not say the last invention, but one of the inventions which is quite heavily being pushed by various researchers. So basically, it returns Zef again if Zef more or equals to 0. This is again linear, becomes on the plus side. But on the minus side, it's alpha multiplied by E Zef minus 1 if Z less than 0. So this is again alpha, the hyperparameter, need to be chosen. Okay, usually it is equal to 1. Default alpha equals 1, and this is quite a good choice for the default. So basically the derivative of this guy would be equal to obviously 1 if Zef more equals to 0, and Gzef plus alpha. Gzef plus alpha. Okay, if Zef less than 0. So this again, this gives a well-defined, not constant derivative on the minus side. So this is F, this is F, A, this is output. And now what we have right here is, again, the linear unit goes like this on the plus side. And here it basically has all the good things that come from well-defined, not constant derivative on the minus side, right? So nicely. And basically, on the minus infinity, it approaches alpha, right? So you basically define how big is the leak, how much of the negatives you want to accumulate, right? So by default, alpha is 1. So basically, it approaches -1, right? This is the amount of leak you want to give. Otherwise, it's basically defined by the researcher. So this is J, and here we have on 1, and here it basically goes down like this, right? It goes down like this, and this is J derivative. Okay, so this is a good thing that it is smooth. Then you need to backpropagate weights on coming from a negative side. So basically, it helps to train more efficiently network. It's slower, but in literature it is said that it outperforms. I've seen the papers that have done various experiments with this specifically activation function, with the leaky ReLU, with ReLU, with sigmoids, etc. So basically, it is always outperformed in terms of the accuracy, final accuracy, plus it faster converged, right? So it's converged faster. So the gain was basically on the performance side and on the speed side. So double gain, why not to use it? It's obviously slower, but it might converge, it might find the optimal values faster. Okay, so this is usage on hidden layers. Okay. All right, so now we need to go into the loss functions and into the neural net architectures. I think I will not be able to cover everything right now. Somehow I'm slow with these neural networks. I thought I will be faster, but it appears that there's lots of things to say. Okay, so what's left for the training of neural nets is basically loss functions. I need to present you some loss functions. Maybe I will do it right now, but not to the end. Then neural net architecture, how to construct the neural net that you want to solve a certain task. Then how to actually construct the experiment with the neural net, and how to fight overfitting. So this is basically, this is enough material for another lecture. So, okay, I think that I will stop here because not much time left. And basically, we can go to any questions if you have. I will stop the recording.